Hey everyone, welcome to Robotics 101. This is part 2 of my 3D printed robot arm series. It's been about a month since I've uploaded my last video. I've been really busy with schoolwork. I had a lot of AP tests and I also take SAT tests, so it's been a while. But in the past 1 month, I've gotten a lot of progress done on the robot. Since you last saw me, I added all my stepper drivers and I was able to add some more electronics and get the motors working, and now I'm mainly working on the software part of the robot. So let's take a look at what I've done in the past 1 month. In the last video, I didn't have the gear setup shown here. Instead, I had the same timing belt and pulley system that you guys will see for the other two axes of the arm. So we can take a closer look and I'll show you how the whole gear system works and how it solved the problems that I was having. So here's a close-up look at the gears. The ratio between the gears is about 2.5 or 2.45. That's what the Autodesk Inventor gear generator ended up giving me. But I also have the gearbox mounted to the stepper motor. I'll go into that once I take the gears off. But I have to swap out the set screws that are currently in the gear for these longer ones, because the set screws that are in here right now are just some really short ones I had at home. So I went out and bought some longer ones because I can add more torque. Like I can use the Allen key and tighten the set screw a little bit more if it's a little longer, and it'll also won't be super. The head of the set screw won't be super close to the captive nut that I have in the gear. So let me get it off and we can take a closer look. These were the old set screws that I was using. These, and I'm swapping them out for these longer ones because before the set screws would go up right to the end of the nut, and if I tightened it too much, it would go past it. And just longer set screws are better for just overall longevity of the gears not slipping. And then I'm gonna show you guys a closer look of the gearbox. This is the shaft of the gearbox. I drilled a little hole. Let's see if the camera can pick it up. I drilled a little hole in the shaft so that when the set screw is screwed in, it'll have like an area to clamp onto, and that'll prevent any form of slippage. Even if the set screw fails, at least they'll have like an area of the metal bolt to clamp onto. And then I have this nylon lock nut holding in the shaft against this carrier, which moves when the shaft of the motor moves right in here. This is just a standard gearbox. I had it linked in the description in the previous video. I'll put it in this one too. Yeah, it's mounted. This plate is mounted to the motor with these screws right here, and then this is a 5-to-1 ratio. So out of the gearbox, I get a 5-to-1, and then with the gears attached on the robot, I get another 2.5, or 2.45. So I get about like 10 gear reduction of about 10-to-1. So that's pretty good for an increase in torque. And I'll show you guys the motor shaft. So this is the motor mount that I'm using with the motor. As you guys saw before, I just had this attached like that. Then I have these two screws with the lock washer attached to them. I only had 2 attached before because for testing purposes, but I'll probably put 4 in the final version. And a closer look at this motor mount. I have these 3 M5 screws screwing down this motor mount to the base. And I also have this extension right here because I wanted to give the motor mount a little bit more surface area contact with the upper part of the base. Because I noticed that before I had that, when the motor was moving the entire arm, the motor mount would move back a little bit. But by clamping it down and having just more contact between the upper part of the base and the motor mount, it prevents the motor mount from moving, and all the rotational motion from the gearbox can be transferred into moving the arm instead of moving the motor mount a little bit. And I have these 2 holes here just in the future. If it ever becomes a problem, I can always just drill holes and put some M4 screws into the motor mount and clamp it down. Now I'm going to move on to working with the electronics for the robot. Let's take a look at how I'm going to mount the stepper drivers and the Raspberry Pi, as well as the main circuit board for distributing all the signals and reading in the limit switches. So this is how I'm planning to have the electronics mounted for the entire robot. I'll have the robot on the right here, all the stepper drivers over there. I'll have my Raspberry Pi, and then I'll have this board which I'll use to connect from the Raspberry Pi to this board, and the board will then transfer the signals to each individual stepper driver. These pins right here on the side are for the end stops, the limit switches that I'm going to be mounting on the robot, and that'll help determine like when the robot is homing and like determine the zero position for the robot. These line of headers right here are the 3.3 volt headers, and they're going to be used for the logic for the stepper drivers. And that's just how I'm doing power distribution. The other form of power distribution is with these two bolts. Let me see if I can get closer. One of them is for ground from the power supply, and one of them is for 12 volts. And each one I'll be using these crimp connectors, these ring terminals from the power supply, using this wire to distribute from the bolts to each one of the stepper drivers. And then the wires from each stepper motor are going to be distributed among the stepper drivers by just mounting it on top and just screwing it in. I might build a plexiglass enclosure for the electronics. That way it'll be enclosed and it won't be exposed for anyone to accidentally touch. Since the last time, I've upgraded the power supply to a 12 volt 30 amp power supply, and that'll be more than enough current. It has more than enough capacity to drive all the motors, as well as the limit switches and everything else that I'm going to be using. In order to properly mount the electronics to the MDF wooden base, I've come up with a little technique that will allow me to easily swap out any electronics if any of them end up failing, or just if I need to do some maintenance on one specific motor driver, for example. So I can show you guys right here. I have an M4 screw that's holding in the stepper driver, and on the bottom I used this wooden boring bit right here, 1/2-inch boring bit, and I created a hole for this M4 nut, and using that I was able to screw in the M4 bolt, and it secures itself against the nut, and it's flush against the wood, so it doesn't hit itself against the surface. And this is really convenient, and it's better than the other option of just threading the wood, because the thread may end up failing, while having a nut on the other side of the wood ensures that the stepper driver won't move and it'll be securely fastened. Now I'm going to repeat this process for the rest of the stepper drivers, and we can look at the whole electronic assembly once it's done. So I'll get started. So since I took the time lapse that you guys just saw, a lot has changed for my mounting base. I've worked on the electronics a lot more. I've done a lot of the wiring. I created my own connectors. So let's take a look at what I've done. So this is the almost completed electronics mounting. I'll show you guys a closer look of each section, and then we can go into detail about each part. You can see my power distribution. I have 2 bolts sticking from the bottom of the MDF, which goes out to each driver, which you can see right there. These wires are capable of handling the current necessary for each motor, so they won't burn up. These are all the signal cables, so from the Raspberry Pi, they'll connect to here. And as I mentioned this before already, so I guess you know what this is. And also down here, I have a power switch for the robot. It's sort of like a simple solution instead of soldering in a power switch. It makes my life easier. So let's go in depth about each part. Starting with the power supply, this is a 12 volt 30 amp power supply, so it's more than capable enough of supplying enough power. I have live, ground, and earth connected right there, and I have some crimps that I bought from Home Depot, having the positive and negative coming out from the power supply. That goes straight from there to these two bolts, which are secured to this base, and we have some more crimp connectors connected to that distribute out into each stepper driver. I just have them screwed in right there for each one. And then we have the Raspberry Pi down here. I've screwed that in as well, so it's decently secure. I didn't want to tighten it too much because I don't want to damage the board. I have the standard power switch that I've been using for the entire time of my debugging and testing, which, as you can see, is connected down there. And this is the main distribution board. This is where everything connects and splits off into. I have some connectors that I'll show you guys here. They're here. These connectors that I made. Let me see if I can. And they go straight from the Raspberry Pi to this board, and then from the board to the stepper drivers. And I have each one labeled with letters like A just for each motor driver, and then like B, for example, corresponds to B, so it's just easier to identify. And my color coding, it's pretty simple. I have yellow as enable, I have blue as direction, let me see, and I have green as pulse, which you guys can see down there. And then I have red for voltage, for sending the logic voltage to each one of the stepper drivers. And that's pretty much it so far. I did some testing with limit switches, and those limit switches will be coming from the robot arm, which will, for example, for the base, the limit switch, I believe the mount, where is it? I believe the mount is right there, and the limit switch will be going from there straight into this distribution, and then again it'll be connected to the robots. The purpose of this board is just to help simplify all the wiring. I have a little test setup rigged here, connected to the Raspberry Pi, so that we can make sure that it can properly read the state of the limit switch and in turn home each axis. So this is the test program I've written. I click enter. Every time I press the button, it should increase the numbers and also say hi. And you guys can hear the limit switch in the background. I am indeed cooking it. So that's pretty much it. Now I have to solder up connections for every limit switch and mount it to every axis, and then we can move on with the software. So let's get started. So it's been about a month since that last clip of me finishing up the limit switches. Summer actually started, so I was really busy with some other activities, but I was able to finish the electronics for the robot arm. Let's go take a look at what I did. And here we go. This is the completed version of my robot's electronics. You guys will notice some things from before, and a lot of new stuff has been added. So here, first off, I have all the limit switches mounted, and they're all nice and soldered and wired up. And I have that for each axis. I don't know if I want to show everyone. You can see one down there, one there, one there. And then all the wires, including the wires for the motors, are going into these like black cable sleeves that go up here and then get distributed for each one of the motor drivers. I also have the wires for the limit switches going through cable sleeves, and then that is like constrained down here, and they all go plug into, let me get this, they all plug into the distribution over there, and from that they are read in by the Raspberry Pi. I also have all the wires for my stepper drivers wired up using the DuPont connectors that I bought from Amazon. I had to custom cut all the wires for those. But yeah, this is pretty much it. I have the power switch for the Raspberry Pi as well as the power switch for the ARM, and most of the components are pretty much the same. I didn't change anything, but this wiring took me a while, so this is a pretty big step forward. After I finished the electronics for the robot, I wrote some basic test code to move each axis of the arm, and I noticed that the motors didn't have enough torque for, at least these two motors didn't have enough torque to move their corresponding joints. And this is a real problem because I don't have any spare timing belts on me, so I can't increase the ratio between the motor and the pulley. So I'm opting to switch to a gear system where I'll be able to easily increase the amount of torque by just changing the ratio between the teeth. So here you guys can see the gears that I'll be using as a substitute for the timing belt and pulley system that's implemented on the robot arm. Let's take a look at the specifics of these gears. If I just pull it up, you can see that the gears have a ratio of 4.5 to 1. The helix angle is about 10 degrees, which is what the slant in the teeth account for. So if you're wondering what that was because I changed the helix angle. The face width of the larger gear is the same as the face width of the current timing pulley that's running each joint, because I wanted to just have like an in-place kind of solution, so that I wouldn't have to buy new axles and it would just be easy to put in. If we look specifically at the parts themselves, you can see that I have mounting holes for the screws so that the gears can just be put in. I have recessed holes so that the head of the screws will be flush with the face of the gear. If we look at the smaller gear, we can see that I have a spot for an integrated captive nut and an M4 set screw. And let's take a look at how it is on the actual robot. So if you guys look here, it's pretty much the exact same way that the old timing pulleys were installed. I just have the motor. It'll be screwed in with these four holes on the plate, on the joint, and then I'll have the motor attached. This gear will be mounted to this arm, and all I'll have to do is unscrew the old one, rescrew this one, and it should be good to go. So let's get those parts printed and installed on the robot. So here you guys can see the gears that I showed you before in the CAD. So let's swap out this timing pulley and get it installed. So here are the gears actually installed on the robot arm. It's installed in exactly the same manner that was shown in the CAD model, with the screws just swapped out. I've also added the end caps, which you can see right there, onto the arms. I've written a bit of test code to make sure that the gears work, so let's see what it does. So I'm actually really happy with the way the gear system turned out. It's a lot better than the timing belt and pulley system that I had before. The arm is a lot more responsive even when I increase the speed of the robot arm, which is great, which means that I can increase the speed and not have to worry about it slipping or falling, which is really, really good. I'm going to be using the same gear system on the third linkage of the arm, which should be good because now we can have all three axes move independently, which will be really cool. In the next video, we'll be working on what end effector, or we'll be designing our own end effector, seeing what works, how we want the robot to interact with the environment, if we wanted to pick up blocks or whatever I decide to do. I know in the beginning of this video, I said we'll be doing a lot of the software portions of the robot,
but I didn't expect there to be some like mechanical issues. But I'm happy we fixed these issues, because now moving forward I can have a consistent robot that does what I expect it to, which is really good. So if you've been liking this series, if you're liking my channel, please consider subscribing and liking my videos. Share it with your friends who are also probably robotics nerds, which is really good. The community is really great, so that's good. Keep an eye out for some tutorials that I'll be publishing soon, CAD tutorials, maybe some electronics or programming tutorials, which would be really cool. So yeah, thank you guys for watching, and I'll see you next time.